when we left, we were down in the optimization world. We are looking at dependencies, dynamic compilers, incremental compilers, in order to speed up rendering. So far so good, but as you remember, I had this timeline some slides before, and at this part we were happy with the performance, but our programs were still kind of spaghetti. So this dependency thing didn't help as much as we wanted to have it. So back to the scratch board, and at that point we found that we really need to look at purely functional concepts and stop with having this middle world. But at that time, we were happy that we have this low-level rendering engine which just works and is the fastest engine we could produce while providing relatively high input descriptions, which is all those inputs are tracked automatically. We can update everything, and we're in good state, and we don't want to look at this low-level optimization stuff again. So now we look at the high-level stuff. At that time, we looked at the Elm architecture. Who is familiar with the Elm architecture? Okay. The Elm architecture comes from the Elm language. It was originally a research project, and at that point, the author found a very simple way of designing applications with interaction part. So it's just a function which is called the update function. We have a model. This is the application state. We have a view function which observes this model, and each time this model gets changed, this view function is executed again and regenerates the user interface. And then we have this view which provides buttons and input possibilities for the user, which triggers an action. The action goes to the update function, and which updates the model, and the view gets updated automatically. So this is like a unidirectional data flow. And I just want to show you a little demo. Or I have it here already. This is a little application. Here is the application. It's just two buttons. We can press plus and minus. And the user interface is relatively simple. It's just, if you look at the Chrome debugger and look at what it is here, it's a div. We have button, we have the text, and then we have a button. So if we didn't see it, but it's just regular HTML which is generated here. If we do a functional modeling by using the Elm architecture, we have a message which is either increment or decrement, one for this button and one for this button. The model in our case is just a simple integer value, so it's no complicated struct. The update message is like, if we get a message, we get the model, we produce a new model and look, okay, is it a message, is it the increment, create a new model of the old model by using the old value +1 or -1, and this is the user interface which with just this function gets executed by the runtime if the model changes and regenerates this user interface each time something changes in the model. And here we have just the buttons which, if it's on click, the message increment is triggered and fed into the loop. Was that kind of clear? It's a super simple concept. It's embarrassingly simple. What's cool here is that since we didn't see any side effects yet, nothing. It's just purely functional, and this can be layered, and we can compose bigger apps from smaller apps by just using function composition. So this thing is nice. But if we look at functional programming, we see that if we have just, this is a dictionary, and the function of the prototype for a dictionary add would be take a dictionary, a key and a value, and return nothing, and add this key value pair to the dictionary. So what's going on here? This is mutation, right? We're changing the data, so we can't use this in a purely functional setting. How does it look in purely functional programming? We have an add function which takes a map, a key, and a value, and returns a new map with this key value pair added to the old map, and the old map still exists. How does this look for rendering? Here we need to create a new map. If we adapt this purely functional scheme to rendering, we have a function which adds an object to a scene and creates a new scene. So we are confronted with new scenes every time. So at some point we need to get rid of those immutable updates in terms of operational semantics in order to feed this stuff into real GPU updates. It doesn't help us to get a new scene representation each time the user moves the mouse. So we need to get it somehow out of this. And this is crucial for big data visualization because this scene can be huge. And if we need to look at every little object in all characters in a game and look if it is changed, we're kind of done performance-wise. So there's one mechanism to handle this. Is like we have a new state, we create a scene representation, then we compute the changes on this, and we feed it into the rendering engine. This is what Chrome does in combination with Elm. Because in Elm, the view function needs to be executed each time something changes. Then they perform a diff on the virtual DOM of the HTML tree, and then they feed this stuff into the machine. And this works because Chrome is awesome. But for GPU data, this is kind of crazier because we need to handle millions of objects, and we need to have asynchronous loading and other stuff, and we're not dealing with a simple user interface, we're dealing with 3D geometry, so we need a better way. And what we found is that this computing changes can be expensive. If we do it like earlier, if we have a new state and compute the change on the state, and then have an incremental scene update, we have this incremental scene representation I introduced before, we are done. Because here we just, in the previous talk, we introduced the best possible implementation of this. And then we have those compute changes on a relatively small state, because the application state typically consists of, in a game characters, level, and stuff like this. But the scene representation contains all little objects within the scene. So here we're in a better state. And how can we do this? What we basically have in a purely functional setting, we have a data type, like just the thing we saw before. We have a model which contains a value, it is an integer. Then we automatically, by using a compiler, we generate a different type which has a dependency graph attached to the value. So this is the entry point for the stuff, for the DSL for dependent computations I showed you just before. And what we need to do is we need a function, it's called apply changes. It takes an old model, a new model, and the model which stays the same. This is the mutated model. This gets mutated by the system and produces nothing. So we only have one function which performs side effects, and then we're done. So we have now a separation between purely functional application level programming, change computation, and then we have incremental rendering engine. How does the code I just showed you before looks like this? This is the old code. This view function gets executed each time the model gets changed. Here in our system we have like the model, we take a view function, we get the mutated model with dependency graphs in it, and we just need to have a mod map function I introduced before. This text element needs to be updated each time this value gets updated. And so we have fine-grained dependency tracking within a user interface code. And we don't need to care. The user interface will always be consistent to what is in the immutable persistent state. So how does this work for 3D graphics? This is a little demo application which just has a single button. This is now interleaved HTML code with 3D code. Here we have a little box, And we have a very simple interaction. We can just switch the model. And this is just the Chrome. As you can see, we have here the Chrome debugger. If we switch the model, we get a new image. So this is the dependency-driven system which carries over to remote rendering and web-based rendering. If we look at the code, we have a functional domain type. We have a primitive. We need to either we render boxes or spheres. And we have a domain model where we have the current model. And then we have a camera, because I just showed you a camera where I moved around. And the application is just the update function in our Elm loop is if we get a toggle model, we look at what's the current model. If it's a box, now it should be a sphere. If it's a sphere, now it should be a box. And we also handle something with the camera. And then we just have, this is like the HTML code I showed you before for having like user interfaces. And here we just have a special HTML element which can be emitted here, which gets a thing of type with named as G. This is called scene graph. And here we have our 3D code which says, okay, what's the current model? With mod map, we have like dependency aware. We add an edge to the dependency graph, and our system knows what to do, right? And if we have a box, we return the 3D model for boxes. Otherwise, we return the 3D model for spheres. And then we put around some shaders by using fshade, where we say we want to have transformations and lighting. And this is all. So it's relatively easy to incorporate the Elm architecture with 3D rendering if we are equipped with a rendering engine which supports incremental changes in a general manner. Like if we have a dependency graph, we know if this thing gets modified, we need to update this GPU buffer. We need this part, and then we have the purely functional part, and we are in a safe world. What if we look at, for example, what do we get of this? If we have like a model for like a modeling tool where we model polygons, then we have polygons we just draw it, and we additionally add a field which is called past, which is optionally, because sometimes we don't have a past, the old model. This is now used for doing undo redo. Like if we edited the scene, edited some polygons, we have it in the list, and each time we want to undo, we look at the past. If is there a past, we return the past with the future, whereby the future is now. And this is the implementation of undo redo for arbitrary complex programs, which also works for 3D content. And I think this is kind of impressive. And we used this whole technology we just showed you before in a project where this is the Mars viewer project I showed you a screenshot from. This is like handling out-of-core asynchronous rendering of big data, of this photogrammetry and other data sources. And we have those geological annotations and stuff in this work going on. And we said, okay, stop. We worked on this program for 5 years. And now we do kind of a crazy thing. We move it completely to functional programming. And we moved it to this Elm-style architecture with this purely functional graphics API with the incremental renderer in which is handling the lower bits. And this was simply because it was too hard for us to maintain the conventional the program written in conventional style. I'll just go quickly over this, but this is the technologies we used for this. And this is basically just the thing I showed you before. We did this for the last year. And it was kind of a great success because we got the program a lot cleaner. Functional programming helped a lot. We now have testable modules which can be composed together. And we just don't need to care about side effects in this big application. So the conclusion for the complete talk is, like, we need to have low-level performance tweaks. We would like to have functional programming everywhere, but the sweet spot is to have like low-level optimizations, doing them smart by using dependency tracking, and having high-level programming languages like the shader language and the incremental language with the mods, and mapping those by using incremental compilers to lower-level bits and having those optimized by the machine. And our rewrite showed that this is good, and yeah, so far we are kind of happy with this architecture. And the most part of the engine and the user interface library and the application framework and everything is open source, and we currently have a kind of wiki landing page stuff. Like here, you can go there, you can use it here for research projects, or you can do collaborations, and we would be happy to do some cooperations as well.